Hey everyone, welcome back to another session with OneClass. My name is Bassam, I'm an engineering graduate, and today we're going to be going through some physics questions at the high school and preliminary university level. So let's get started over here with the first question. Okay, so we're gonna look at the question and then look at the junior tutor's answer, and then we're gonna try to verify the answer and go through the correct process on how to get the solution. So this first question gives us a plot, angular displacement on the y-axis, and then time in seconds. The first question, part A, what is the angular displacement of the wheel between time equals to 5 seconds and time equals to 15 seconds? And then part B, what is the angular velocity of the wheel at 15 seconds? So we're trying to evaluate for these two components based on this plot. So going through the junior tutor solution, so we have here, we can extract the following information from the angular displacement versus time graph. So they correctly go through the first step and they look at the graph. So at time t equals to 5 seconds, they get 100 radians, and time equals 15 seconds, they get 125, and then they take the difference, get 25 radians, and then here they show that this is in the clockwise direction. And then for answer B, the angular velocity of an object is given by the rate of change in the angular displacement of the object. It is slope of the angular displacement versus time graph. So they've correctly defined the angular velocity, and they've taken the slope based on the graph, and they obtained 5 radians per second anti-clockwise. So let's go through this step by step to figure out how to go about the right process and then if this is the correct solution or not. So this is question number 1. So part A. So let's go back to the question. What is the angular displacement of the wheel between time equals to 5 seconds and time equals to 15 seconds? So displacement here, we're not looking at distance traveled, so it would be just taking the difference between those 2 points at those points in time. If it was distance traveled, then we'd have to do a different calculation, but here we're just looking at displacement. So at time equals to 5 seconds, if we look over here, at 5 seconds we have 100 radians, so we'll say, so here we'll say at theta when time is 5. So here we have theta t, and we're trying to evaluate at theta when time equals to 5, and we get 100 radians. And then here at time equals to 15, we can see that this is about 125. So 15 equals to 125 radians. So here we do final minus initial. So the final at time equals to 15 minus the initial at time equals to 5. And we have theta 15 minus theta 5 will be equal to 125 minus 100. And we end up with positive 25 radians. So to assign a clockwise or counterclockwise for this, so whenever you're looking at, let's say, a coordinate system, you always take the counterclockwise direction as positive. So we'll say counterclockwise is positive, and then clockwise direction is negative. Clockwise is negative. And this is for, that's just the standard for physics problems. So here, because we have a positive value, we'd say 25 radians counterclockwise. And that would be our answer for part A. So let's look at over here. So here they have 50 radians clockwise and 25 anti-clockwise. Interesting. The net displacement of time equals to t to 15. So I'm trying to figure out what they did here. So they initially had this angular displacement. So I believe the question was asking for angular displacement, which is correct. So here the direction of the angular displacement can be found, rotation of the wheel. The wheel rotates 50 radians clockwise from t to 5 to t to 10. So angular displacement is increasing. And then angular displacement is decreasing. So since we're asked for displacement, not necessarily like the distance traveled, we'd only really care about the 2 points here. So really we only care about at time equals to 15, at time equals to 5. So although this is showing an increase and a decrease, really it's only from here to here, which is an increase. And that's why you would get counterclockwise rather than clockwise. So they get the right value but the incorrect direction. Alright, let's go to part B. So for part B here, so here we're looking at what is the angular velocity, and we equals to 15. So at 15 we want to know the angular velocity. So we're given an angular displacement versus time graph, so here angular velocity would be just the rate of change of this slope right here. Because we have a straight line, we can kind of just take 2 points on this line and do the rate of change. So we know that the angular velocity at times equal to 15 will equal, so we'll take rise over run. So we'll say this is the final point and this is the initial point. So at the final point we have the y-axis is 100 minus at the initial point the y-axis is 150. And then we have the x-axis here, so final point is 20, and then initial point is 10 seconds. So we just took final minus initial to do the slope, and we did essentially kind of rise over run. So here we take the y-axis, 2 values at the y-axis, and we get 100 here for this point, and then 150 here for this point, and then similarly 20 for this point, and 10 for this point for the x-axis. And we end up with negative 50 over 10, which gives us negative 5 radians per second. So let's scroll down over here. So angular velocity at 15 seconds, so they do similar calculation, they end up with negative 5, and then they give the anti-clockwise direction for a negative. So this is kind of just switched around, so this should be anti-clockwise and this should be clockwise, because as we said, for a coordinate system the counterclockwise direction is positive and then the clockwise direction is negative. So here we would say clockwise. So actually we would say 5 radians per second let me just erase this, write it a little clearer. So radians per second clockwise. That's our final answer for part B. So we'll write a comment here. So correct answer and process. Part A should be counterclockwise and part B should be clockwise. The directions are inverted. Okay, and we'll mark this as correct, and we'll move on to the next question. So this is question number 2. So here we're asked, how many times does a typical person blink her eyes in a lifetime? Excuse me. So here, let's just go through what the junior tutor responded to this question. So here, determine blank the typical. So there's some missing words in this solution, so it seems like there's an incomplete solution. But this is essentially the concept that we're trying to address in physics here is a Fermi estimate. So Fermi estimate. And essentially what a Fermi estimate is estimating for some kind of scenario. So in this scenario, we're trying to estimate how many times the typical person blink her eyes in a lifetime through a Fermi estimate. And we start off with something very small and grow that bigger until we get to the lifetime. And it'll be very close to what the actual number truly is, but we're using this Fermi estimate process to get very close to that number without actually calculating all the minuscule values. So we can start off with just thinking about how many times does like a person blink, like once, let's say. So we can say that approximately we would do one blink every 5 seconds. So one blink every 5 seconds. And that's kind of just an estimate. You could be a little higher, you could be a little lower. You could think about it per minute as well. But for just this question, I'm just going to think about it this way: one blink every 5 seconds. And then since we've kind of reasonably thought, okay, it could be a true scenario, we can just build that up over a person's lifetime and calculate how many blinks they would do. So this is our estimate here. So we would say one blink every 5 seconds. And then we can multiply that with how many seconds are in a minute. So we'd say 60 seconds per minute. So here we have seconds, and then we'll multiply that again by 60 minutes per hour. So essentially we're just trying to convert it using just conversion rates until we get to the lifetime. So now since we have 60 minutes per hour, we can multiply this again by 24 hours per day for 1 day. Put a 1 over here. And then we'll multiply this again by 365 days per year. And this is days. And then finally, just thinking about the average lifespan of a person, you can say on average someone would live up to 75 years. So we'll multiply this by 75 years. And now we've kind of approximated about how many times someone will blink in their lifetime. So you can see that the units cancel out. So the seconds will cancel out with seconds, minutes with minutes, hours with hours, day with days, and then year with years. And then we'll end up with just the unit, the number of blinks. So we'll do this calculation. We'll use our calculator over here. So we'll say 1 divided by 5 times 60 times 60 times 24 times 365 times 75. And then we end up with the following: 473040. We'll put commas, 000. So about 473 million blinks in their lifetime. So this isn't like an accurate answer, but it's an estimate. So you would be in the ballpark of how many blinks this person would be in. So you could also say that since there's about, let's say, 5 times 10 to the 8, because we have here 1, 2, 3, 4, 5, 6, 7, 8. So we could say 5 times 10 to the 8 blinks, or we can just say 10 to the 8 blinks about. So this is roughly how many blinks. So you've gotten some kind of estimate to how many blinks someone would blink in their lifetime. And that's how you go about solving this question. So we'll say incomplete, solution incorrect. Okay, and we'll mark this as incorrect. Let's move on to the next question. Alright, so the question here is asking us, why does lifting one end of a track lead to constant acceleration? So let's look at what the junior tutor said here. A straight track can be idealized as a line to help simplify and quantify the thought experiment. So this is question number 3. Let me just write that down so I don't forget. So the thought experiment lines are defined mathematically by their slope, its rate of change, or how steep the line is. Lines in mathematics are 2D, have an exponent of 1, and are called linear functions because a line has constant slope. Although the speed or velocity increases as it moves along, it does so at a constant rate, and its graph is that of a line because its acceleration remains constant. The rate of change of a line is also constant no matter how high you lift the track. The velocity's graph is a line, and its rate of change acceleration is constant. So this is a good explanation. But let's draw a diagram just to think about what's going on. So if we had some kind of straight track, we had it like this. So we'll say this line is a track, and we had some object. So essentially what we're doing with this track is we're lifting this one end. We're just lifting this up. And the object will eventually start moving this way. So the next scenario would be that the track will be at an angle, and then we have the object over here, and then we keep lifting the track, and then the object starts sliding down. And here it's asking, why does lifting one end of the track lead to constant acceleration? So to understand why it's constant acceleration, you have to think about what's going on right now. What are the forces acting on this object? Why is it moving? So here we note that there's always the force of gravity and then acceleration due to gravity. So we know on this object there's the force Fg, the force of gravity, and then we have the normal force on the object. So we're drawing the FBD, free body diagram, and then we might have a friction force, or we might have something else here. So the main thing to note here is here for the force of gravity we'll have a y component here. So if we had a coordinate system like this at an angle, an x and a y, we'd have a y component to the force of gravity and an x component. So this would be fx and fy. So we can see based on this, we know Fy is only equalized by the normal force, but here we have Fx, which is the reason why this object is accelerating. So we know F net equals ma. So this is Newton's second law. And then we can see that this Fx is not countered by anything unless there was a force of friction, and this Fx is caused by the force of gravity, and the force of gravity is caused by acceleration due to gravity, and that's at 9.8 meters per second squared. And since this value right here is constant regardless of the situation, we know that this force of gravity on the object will be the same, and then thus Fx causes this object to move with constant acceleration due to the constant force of gravity of acceleration acting on it. So that's kind of a way to conceptualize what's going on, to understand why lifting just one end of the track causes this constant acceleration, and this is mainly just due to the force of gravity and the x component acting over here. So we'll mark this as correct, so correct answer, great job. And let's move on to question number 4. Alright, so here's the full question. The winner in a tug of war exerts the greatest force on blank. So they just fill in the blank, and we're trying to figure out the winner of a tug of war situation, where do they exert the greatest force? Excuse me. Alright. So let's look at what the junior tutor wrote over here. In a tug of war, the force exerted on the rope by both teams is the balance force with no acceleration of the rope in either direction. If the teams want to win, then the greatest force is to be exerted on the ground for all of them to accelerate backwards. Because at any force on the rope will be equal for both teams, but to win the game, forces on the ground is responsible. Ground is considered to be the point of support for both the playing teams, and losers will be thrown away if they cannot withstand the torque. So this is the correct answer, but let's think about this conceptually, how this makes sense. Why is it the ground that the greatest force is exerted on? So if we had, let's say, some person in a tug-of-war situation with a rope, and they would be kind of just pulling on the rope, but we know that the point of support will be on the ground. So we have the ground over here, and they're supported by their feet. So although they're pulling on the rope, the only reason that they're able to do so is because of they're pushing, essentially they're applying a force on the ground, because usually you think that your feet are pushing, they're applying a force this direction on the ground in the x-axis. It could be like more of an angled direction, but we'll look at it in the x-axis. And then from this we know that there's a reaction force from the ground that pushes back, and the ground pushes back on the person who's pulling the rope. So essentially, basically, because there is when they're pulling on the rope, really the force that's exerted is on the ground, because that's where you're being supported. Although you're pulling on the rope, which has some force of tension, and then there's another force of tension that's pulling back on the other side. We know that the winner of this situation would be whoever pushes on the ground more, which would essentially help them pull the rope even more, and then it would make the F net in their direction. So the F net direction will start pulling in their direction, because they're applying, or they're exerting, the greatest force on the ground. And that's how to think about why it's the ground that the winner in a tug of war exerts on. The greatest force is on the ground. So we'll mark this question as correct. Great job. And we'll move on to the next question. So this is question number 5. Alright, so what represents the impulse of a force in a graph of force versus time? Okay, so let's go through what the junior tutor answered here. Excuse me. The area under the force time graph represents impulse. So right away, this is kind of the correct answer, but they go on to explain it's calculated as force multiplied by time. It is a vector and calculates the force that is applied over a particular time to an object. It acts only for a short time and can be used to find a change in momentum. This has several applications in automobiles, sports, collision impact. So this is true. So let's look at a force versus time graph. So if we had some force here, time t, and then some force applied. So we could potentially have, like, let's say there's something like this. So this, let's say this is the plot that we're given. And we're asked to calculate the impulse of this situation here with this plot. So essentially what you'd have to do is figure out how to calculate the area here, the area here, and the area here. And that will give you the impulse. And the important thing to note here is the areas above the x-axis, so they're in the positive area of the y-axis, you would have positive values, but whenever you're above the x-axis, these would add to the impulse total sum, and then when you're below the x-axis, this area would be subtracted from the total. So if you had, let's say, let's call this I for impulse, and you had A, B, C, and you had A, B, C, you would do minus plus. So you'd add A subtract b, and add c. So this is above, this is below, this is above, and that's how kind of the summation would work. And then here you'd kind of, if they're just in triangle forms, you would just do the kind of the area of a triangle, half times base times height, and so on. So this is the correct answer. So correct answer, great job. And we'll mark this as correct. Let's move on to the next question. So here we're asked, what physical property does the symbol IENCL represent? So let's look at what the junior tutor answered here. It is the amount of current flow through an electrical circuit. I equals amount of electrical current, and ENCL is the short for enclosed. So this is the correct definition. Essentially, this is associated with Ampere's law. So this is question number 6. Ampere's law. And the equation for this is the path integral of as follows. So here, which will be equal to constant times IENCL. And this term over here is what we're referring to when we're talking about I enclosed. And essentially, just to write out what this is, I enclosed is the net current that crosses the surface that is defined by the closed path. So we have some current going through some wire, there's a closed path situation, and essentially this is the current over here in this equation, in Ampere's law equation, and you use that current to calculate if you had some kind of givens, etc. So this is kind of just the general definition of what IENC represents. It's the current enclosed in the closed path defined by this integral for an electrical circuit. So we'll mark this answer as correct. So correct answer, great job. And we'll move on to the next question. Okay, so this is question number 7. Alright, so in uniform circular motion, which of the following quantities are constant? So we're given 4 quantities: speed, instantaneous velocity, centripetal acceleration, and the magnitude of the net force. So let's just write these down. So speed is our first one. And then we have instantaneous velocity. Instantaneous velocity. And then we have centripetal, so I'll just write short form, acceleration, and magnitude of net force. So we'll just call this F net. Okay. So let's look at what the junior tutor answered here. So when an object revolves in a uniform circular motion, the speed of the object remains constant as the object equal distance in equal intervals of time. However, the direction of the object continuously changes. That is why the velocity is not constant. The object covers equal angular distance in equal amount of time, which makes angular velocity constant, and the angular acceleration becomes 0. Centripetal acceleration varies for the velocity, and the magnitude of the net force on the object is the same at all points. Thus, speed, angular velocity, and the magnitude of the net force remains constant in uniform circular motion. So we have speed, so they're saying speed, angular velocity, and the magnitude of the net force remain constant in uniform form. So we're not here really asked about angular velocity, we're asked about instantaneous velocity, and I believe they mentioned this up here. Time, velocity. velocity constant, angular centrifugal acceleration. Okay, so if we're looking at kind of just an object moving in a circle, so we have, let's say this is the center of a circle over here, and we have this kind of path. Let's say this is a bad circle. Let's say it's a perfect circle. We'd have some F net force. Let's say the object was over here, and this would represent the centripetal force. And the object moving, let's say in this direction. This is the instantaneous velocity, so we draw that tangent to the circle. So we can think about speed here. So because we have uniform circular motion, we know that the speed, which has no direction, we're only thinking about magnitude when we talk about speed, throughout the entire motion around the circle, it would be the same. It would never change, because we have only this centripetal acceleration, which is acting on the object to move in a circle, but there's no change in speed of the object throughout the situation. So the magnitude will stay the same. The direction of the object changes, for sure, but since it's uniform circular motion, the magnitude of the velocity stays the same. So for this, we know magnitude stays the same. So this will stay constant. So let's think about instantaneous velocity. Since we're saying velocity, not speed, we know that instantaneous velocity has a direction. And instantaneous velocity is represented by this arrow over here. So let's say when the object moves to over here somewhere, we'd have another dot, and this would be instantaneous velocity now. So it would be this at this point, and then this at this point. So we can see that the direction has changed. As we're talking about velocity, we're talking about magnitude and direction. We can see that the magnitude is the same, but the direction has changed. So therefore, in this situation, you would say instantaneous velocity is not constant for uniform circular motion. So let's look at the next situation. So centripetal acceleration. So for centripetal acceleration, it would be AC. So it would also be acting in this direction as well. And throughout the motion, let's say the ball was over here now, centripetal acceleration will be in this direction. So once again, same idea. So since it's centripetal acceleration, it will have a direction and a magnitude. So here we can see when the ball or object is at this point, the centripetal acceleration points this way. And then when it's at this point, the centripetal acceleration points in this direction. So if I were to draw like a better circle, what I was thinking, like, it would be something more like this. So this is kind of not a perfect circle over here, but think of it as a perfect circle, and that these two arrows are tangent, and then these two arrows, this arrow and this arrow, are perpendicular to that tangent line. And we can see that for centripetal acceleration, there's a change in direction. There is no change in magnitude, but since there's a change in direction, we know that this is not constant. And finally, we have the magnitude of the net force. So we can see here, we'll put kind of an absolute value. So since we're talking only about the magnitude of the net force, you can see clearly that they've specified this for a reason. We can see that although the net force changes direction, so the next net force will be over here. This would also be F net. So I'll say that's F net. This arrow over here. You can see that similarly to centripetal acceleration, the magnitude of the net force changes direction. The net force changes direction, but the magnitude stays the same. And since here we're asked for the magnitude of the net force, we would say that this is also constant. We don't really care about the direction, since that's not specified. So based on this, they specify the correct answer. So angular velocity we're not really asked for, but this is also true. The angular velocity is constant, magnitude of net force is constant, and speed is constant. So we'll mark this as correct. Correct answer. Great work. And let's move on to the next question. So question number 8. So here, what the question is specifying is if we rub electrons from our hair with a comb, the comb will become what? So really for this question you only really have three options. It's either positive, negative, or I guess we'll say N for neutral. So only three options for what the comb becomes. So let's look at what the junior tutor answered here. So when two objects come in contact with each other, then electrical charges are exchanged and the positive charges are built on one object and negative on the other. This is also called the building of static electricity. So this is the term for this, what's going on, static electricity. When hair is combed with a comb, the unwanted electrons from the hair go into the comb and hair gets positively charged. Now both hair and comb attract each other. After combing, the comb becomes negatively charged because each material has a tendency to lose or gain electrons. So here we have electrons from your hair with a comb. The comb becomes negatively charged. So here we would have something like this. Let's say we have a person with lots of hair, and they have some comb. Let's say this is a comb, and it has spikes. And let's say when they're in contact and they're combing their hair, you'd have, since the question has kind of set it up where it says rub electrons from your hair with a comb, they're kind of indicating that there's a bunch of electrons in your hair and they're moving to your comb because the force of friction, they're rubbing between each other and it's causing the electrons to move. So we end up with a more negatively charged comb and a more positively charged hair. And since this is the situation, we've kind of lost, since we're losing electrons, we're losing negative charge, and that's what's causing the hair to become positive. And since the comb is gaining negative charge, it becomes negatively charged, and then the hair and comb are attracted. Here we're only really asked for what does the comb become, and then our answer here is negatively charged. Negatively, one second, so let's see, negatively charged comb. So this is the correct answer. Great job. And we'll mark this as correct. Alright, so question number 9. Alright, so in this question we're asked, do the magnetic field lines really start at the pole face? So let's go through what the junior tutor said over here. Magnetic field lines do not start at the pole face. In fact, they are continuous. They do not start or stop. They just circulate around their source, also called flux lines. So there's another term for magnetic field lines. These imaginary lines originate at the north pole of a magnet and end at the south pole. The motion of magnetic fields is the source of magnetic fields. Just like electric fields, they are also classified as vector fields that have a direction and varying strength at different points in space. Magnetic field lines are different from electrical field lines as they originate and terminate on the source of the charged particle. So let's think about this with a diagram. So if we had some magnet, and we had kind of the north end over here and the south end. So we'll use blue to represent the magnetic field lines. So we know that for a fact that they originate from the north end and enter the south end. So they come from the north end, and then there's a bunch of these around. So you'll have more. So we're just using a couple just to represent. But what actually happens is they don't really start or end. It'll actually just end up going all the way through and back again. So you can think of them as just kind of loops through the magnet. So the statement would actually be Also, do the magnetic field lines really start at the pole face? So this is incorrect. Really, they're going all the way through. They're kind of going all the way through and looping back around to the South Pole. So exit from the north, enter through the south, and go back and exit from the north again. And this is kind of what the Junior Tutor is explaining here. So we'll say here correct answer, excellent work. And we'll mark this question as correct. Alright, so question number 10. Okay, so for this question, we're asked the following. Two wires lie perpendicular to the plane of the paper and equal electric currents pass through the paper. So we have two wires that are lying perpendicular to the paper, and we have equal electric currents. Point P is equidistant from the two wires, so at a same distance from each wire. All three components create what looks like an equilateral triangle. So they're in a triangle format. So they look something like, let's say we had one wire, or we'll say X, that means the wire is going into the page, and then we have another wire that is also going into the page. So when there's two kind of formats to represent into the page and out of the page. Into the page is like this, out of the page is like this. So when you have this, you know that the wire is going out of the page and the current is coming at you, versus when it's an X, you know that the current is going into the page. Okay, we'll continue on. So P is an equidistance, and they form kind of an equilateral triangle. So we'll say point P somewhere over here. So number 1, construct a vector diagram showing the direction of the resultant magnetic field at point P. Explain your reasoning. If the current in both wires were instead directed out of the plane of the page, show the resultant magnetic field at point P. So essentially, what we'd have to do is use kind of the right-hand rule to figure out the vector for the magnetic field. So let me just so let me just double check something over here. Alright, so essentially, to figure out the direction of the magnetic field, what we'd have to do is kind of the right-hand rule. And to do this, you would essentially kind of, if you just take your right hand, and when you're looking at, let's say this, you would point your thumb into the page and look at where your fingers are rotating. So if we point our thumb into the page, we can see that our fingers are rotating in this direction for the first wire. So this is wire 1, we'll call it wire A, and this is wire B. So for wire A, we can see that the magnetic field is acting in this direction. So whenever I kind of think about what direction, so B here represents magnetic field. So if we take just the perpendicular line over here, so if we had some line kind of like that, and say this is at a right angle, so this isn't really at a perfect right angle. Let me just redraw this quickly. So if we had something like this, you can see that using the right hand rule, so you take your hand, you point your thumb into the page. So for me, it's kind of going this way. So, and your fingers curl around to kind of, they curl in this direction, and you can see that the tangent here from this line will point in this direction. Similarly, if we did the same thing for this one, you can see that, so this isn't the best equilateral triangle, but essentially you'd see that it would point in this direction for B, B. And there's a right angle over here. So you do the same thing with the right hand rule. Your thumb would be pointing into the page, your hands curl around to show you that it's in this direction. And then since these are equal electric currents, we know equal electric currents will give us equal magnetic field. So each wire provides an equal magnetic field. So we can see from this, each one will have a y component and an x component, and a y component up here and an x component. Since B, the magnitude for the magnetic field of the first wire and the magnetic field of the second wire are equal, we know that the y component cancel out, because here we have a positive y. Let me just draw a coordinate system. So we'll say that something like this, x, y. So upward is positive, and then downward is negative. These cancel out, and then we have negative x plus negative x. So we know the result will be something like this, and that will be the result. So we'll call this net, Bn. And that will be the direction that the magnetic field points in. So let's think about so this is the first scenario. Construct a vector diagram showing the direction of the resultant magnetic field, point P. Explain your reasoning. We kind of went through the process with pointing to this direction. Let's think about, let's say it was pointing in a different direction. So we'll erase this to make some space. I want to keep both diagrams just to show you what I mean. So we have, let's say they're into the page, and we have point P over here. We'd use the right hand rule again, so you'd use your right hand, but this time your thumb is pointing out of the page. So really, when you have your thumb pointing out, you see your fingers will curl in this direction, and it will go this way, because this is the perpendicular or the tangent line. So if we drew kind of just a line like this, the tangent line will be in this direction, and then that's the, let me draw that a little clearer. So this is the direction of the magnetic field for the first wire, and then similarly for this wire, use the right hand rule, and you end up that it's in this direction. These are right angle. So I didn't draw that really very nicely. So really here, let me draw that a little better. Put a dot here. So like that. There's a right angle. And then you have kind of, so this is the magnetic field for this wire, and this is the magnetic field for this wire. So we have same idea, A and B again. So A magnetic field, A magnetic field is this one. B magnetic field is this one. We know that the y components in this direction, and the x component, the y component, and x component. We can see that there's positive y cancelled out by negative y, since we know equal electric currents means equal magnetic fields, and then we have a positive y, a positive x and a positive x. These add up. We know the resultant would look something like this. So I'm over exaggerating the line, but essentially this would be the net magnetic field of the direction of where it will be pointing at. So I've kind of over exaggerated the line, but it should be a little shorter, but that's kind of the direction it should be pointing at. So here we're not really provided with a solution from the junior tutor, so we'll mark this as the incorrect answer, or incomplete solution, no answer present for part A, net magnetic field points to the left if both currents of the wire are going into the page. For part B, net magnetic field points to the right. And we'll mark this as incorrect. Alright, so for our next question here, this is question number 11. So here we're asked how many valence electrons does helium have. So for helium, we'll have kind of the following. So we'd have, so this is more of a chemistry question, not a physics question, but we'll answer it anyways. It's a pretty straightforward question. So here we have, if you look at the periodic table, we'll have an atomic mass of 4 and an atomic number of 2. So to figure out the number of electrons in the valence shell, you can kind of just kind of look at this number over here. So essentially, since we have 2 protons, we'll have 2 electrons, and that kind of tells us that's kind of an easy way for helium. For other atoms, you might have to look at the columns to determine the number of valence electrons. So let's look at what the junior tutor wrote over here. Helium is located in period 1 and has an atomic number equal to 2. Therefore, neutral helium will only have 2 electrons in the surrounding nucleus. So because for helium, if it's a neutral atom, we'd have 2 electrons if it has no charge. Valence electrons are the electrons located in an atom's outermost shell. So this is correct. The peripheral shell of a molecule can accommodate a maximum of 8 electrons. It was seen that a molecule of elements having a totally filled furthest shell show minimal compound movement. This is kind of a further explanation of what's going on. So we can go further. We know that atomic number of helium is 2, so it only has 2 protons and 2 electrons, as the charge of the electrons and protons are equal. So because for helium, the charge of the electrons and protons are opposite, so positive and negative, so we know that there's 2 electrons to make a neutral helium atom. So yeah, so they go on to explain this a little further. Really, for this question, how many valence electrons does helium have? You only really need to say there's 2 electrons. It's not a very complex question. What is the valency of sulfur? Valency of an element is its combining capacity, so electron configuration of sulfur. We have an atomic number 16. So to attain stability, you would have to gain 2 electrons. As a result of combining capacity of sulfur has a valency of -2. So because it has a total of 8 electrons in its shell, sorry, not 8 electrons, 6 electrons in its valence shell. For it to be neutral, it would need 8. So here we'd say it would have -2. It has to gain 2 electrons. So the combining capacity of sulfur as valency is -2. So let me just look at this real quickly. So I'll just look up the periodic table. So kind of looking at this, you can see that, say for sulfur over here, you can see kind of just looking at each group, we have for this group, we'd have 1 electron in its valence shell. Here we'd have 2, here we'd have 3, 4, 5, 6, 7, and then helium is special, we'd only have 2 electrons. Here we have the rest have 8 electrons in its valence shell. So that's kind of a way to think about how many electrons are in the valence shell for these atoms. So here we'd say 2 electrons is the answer. So say correct answer, great job. And we'll mark this as correct. Alright, so the last question we're looking at is question number 12. So if a car is moving to the left with constant velocity, one can conclude that blank. So we have constant velocity. Okay, let's look at what the junior tutor said. When an object moves with constant velocity, its acceleration is 0, and hence the net force on the object is also 0. So when we're looking at F net equals ma, we can say that since acceleration is 0, so at constant velocity we know a is equal to 0. And based on this equation, we would also can say that f net must equal 0. So here, as we know, acceleration is a equals change in v, so we know a is change in v over change in t, so change in speed over change in time. At constant velocity, the change in speed will be 0, so this will be 0, and that gives us the acceleration equal to 0. Hence the force F net equals ma. F is the force, m is the mass, a is the acceleration, will be 0. So here, what are we asked over here? So if a car is moving to the left with constant velocity, one can conclude that, I guess this is kind of more open-ended, but essentially we can conclude that since there's constant velocity, there's zero acceleration, and the net force has to be 0 on the object. So I guess that's what we're going for based on the solution provided by the junior tutor. So essentially, we would end up with net force should be 0. So regardless of direction, here or there indicate left, but regardless of direction, if an object is moving at constant velocity, this will always be the case. And this can help you kind of simplify solutions and your equations. So correct answer, great job. And we'll mark this as correct. Alright, well, thank you for tuning in to this session. Hopefully you found this helpful. If you need any more tutoring needs or homework help, you can always visit OneClass.com. You can also visit the link in the description, and you can also subscribe to see more videos like this. I'll see you in the next session. Goodbye for now.